So let's take a look at some of the tools you'll use in a PRA. We'll look at an event tree, which is the analysis technique for identifying and evaluating the sequence of events in a potential scenario following an initiating event. And then we're also going to look at fault trees, which we can use to help determine the cause or failure, or we can test the reliability of a system by stepping through a series of events using Boolean logic. So as I said, the event tree is a graphical depiction of a sequence of events. And so let's take a look at how we could apply this event tree to a small break, loss of coolant accident, or what's known as a LOCA. So most event trees are laid out just like this, and along the top we're going to list the phases of an event. So in the case of a small break LOCA, we're going to start with the initiating event, which is the LOCA itself. And then we move along the progress of the event, listing the mitigating steps until the system either fails or is okay. The end states are listed on the right-hand side of the event tree. You can see that here. So after a LOCA happens, the reactor should automatically trip. And this basically drops the control rods into the core to retard the fission process. And if the event is successful, then you're going to follow the path on the top. And if it's not successful, you're going to follow the path on the bottom. So for this case, let's assume that following the LOCA, the reactor trip is successful. After the reactor trips, the high pressure injection should occur. And so this process pumps new feed water into the core to help keep it covered. And so just remember that if you are not familiar with this, a LOCA means that water is basically draining from the primary system. And your objective is to keep the core covered so it doesn't overheat and melt. Let's say for this case that the high pressure injection fails. And now pressure is still being reduced in the core, basically because there's a hole in it from the break, right? But the next step is to initiate low pressure injection. So let's assume that low pressure injection also fails for whatever reason. And so at this point you can see that if we follow the chain of events, we're going to have core damage, right? So not a good outcome. At this point, most engineers would be asking, okay, so what would be the cause of this safety mitigation systems to fail? And for example, why would low pressure injection system ever fail? And what's the probability of something like that happening? And so that's where the fault tree comes in. So the main purpose of this fault tree analysis is to help identify potential causes of system failure before the failures actually occur, right? Because it's a top-down deductive failure analysis that uses Boolean logic. Basically, it's a top-down deductive failure analysis that uses Boolean logic to combine these lower-level events. And again, if you're interested in getting a little more background on fault trees, you can just click this link on the slide where it says Learn More. So let's look at this basically simple system here. In this case, the goal is to inject feed water into the rapidly heating core. So we have a water tank on the left, 2 pumps in parallel which are pulling water, and then 3 valves also listed in parallel on the right. So the success criterion for this system is for water to flow from the tank to at least one of the 2 pumps, and then to at least one of 3 working valves. We would also ask more specific questions like how much flow is needed to remove what is the decay heat, or how much flow is necessary to restore inventory to the core, inventory being basically water, feed water. So failure occurs when we're either not getting any flow from the tank, or the pumps aren't working, or the valves aren't working, right? This process will also force us to ask questions about supporting systems needed to prevent this type of failure, like electrical power needed to energize the pumps and the availability of seal and cooling water for the pumps. Okay, so from our system diagram on the previous slide, we can start to logically break down the event into this fault tree. So at the top, we have a failure, and at the very bottom, which is denoted by the circles, we have these initiating events. So the boxes, the blue boxes, indicate a very basic event. So this could be an equipment failure or even a human failure. For very basic events at the bottom of the tree, we need to have data to indicate the likelihood of those events. And then as we move up the tree, the higher level event likelihoods will be calculated. So if you recall Boolean logic, you remember AND gates and OR gates. And again, we won't go through these here, but you can reference the fault tree link I mentioned a few slides back if you need help. We can walk through one event chain just to see how the low pressure injection system might fail. So starting at the top, the low pressure injection could fail if any of the input events fail. So this means if the pumps fail, or if the tank fails, or if any of the valves fail, then low pressure injection would fail, right? So again, this is denoted by OR gates, which look kind of like the arrowhead with the pointy tip. So what would the probability be that the pump system itself could fail? Well, either both pumps could fail independent of each other, or the pumps could fail by a common cause. So in this scenario, we're not breaking up the common cause failure, although you could. Instead, we're just going to assume a single likelihood of that event. Possibly this could come from, operating analysis or from a completely separate analysis. The next question is, so what's the probability that pump A and B fail independently of each other? Basically, what's the probability that both pump A and pump B fails? And again, this is a simple example, and we've kind of just assumed that those probabilities are known. So you may be asking, how do I set one of these fault trees up? I mean, these things can really get quite complex. And what we would typically do is set up a fault tree by identifying what's known as cut sets. So for example, at the top you can see that there are three main events that were identified to cause the failure: the pump failing, the tank failing, and the valves failing. If you remember that system diagram from before, it should sort of make sense. And I've included it again here. Remember that we had the tank, the pumps, and the valves. So if you isolate those components according to their subsystems, then the problem becomes a little easier to solve. Basically, these are groups of failures. Cut sets are groups of failures that, when put together, result in the overall failure of a system. So now that we talked a little, we did talk about this a little bit before, but it's important to understand where we get these failure rates and these probabilities. Basically, where does this data come from? So I wanted to point out that what we're about to talk about is not exclusive to nuclear engineering, but really applies to most mature industries. So if technologies in the system have been around for a while, we can often look at operating experience to gather data on the frequency of initiating events, failure rates of plant equipment, average availability of plant equipment, and probabilities associated with repair and recovery efforts. In some cases, we may need to look to industry experts for estimates of very rare events. And also, as we highlighted in this course and module, we may have to conduct human reliability analysis to get estimates of the likelihood of human operator failure. Lastly, we can look at specific modeling techniques such as common cause failure modeling to get data. So in the next lecture, we'll work through a very simple example of an event tree and fault tree analysis, just so you can get an idea of how to apply these methods in real time.